All right, guys, let's get started. The topic for today is graph partitioning algorithms. So we're gonna look into the ways you can split the graph based on a certain criteria. And this is, lecture number one out of series of lectures dedicated to this topic. In fact, we're going to be using some of the knowledge we're going to learn today later on when we start talking about community detection. So what's graph partitioning? Well, graph partitioning is just a split or division of a graph into subgraphs by partitioning set of nodes into mutually exclusive groups. So for example, I can say, okay, these nodes form one group and the rest of the nodes form another group. And in this sense, I partition graph into this one and that one, right? I split the graph into two pieces. Or I can say, okay, this is the nodes for one group, right? Say the rest is for another group. And then this is one non-overlapping set, and this is another non-overlapping set. Or even more, I can say, okay, look, this is one set, right? This is also a valid graph partitioning, a valid split of graph into two, into two subgraphs where nodes are mutually exclusive. All right, okay. So that's graph partitioning. Now, when we start looking at the graph partitioning problem, you typically do not just cut the graph into pieces. You typically want to satisfy certain constraints or certain optimization criteria, right? You want to do it for a reason. But overall, there are lots and lots of ways of doing this split. And if I want to solve, for example, for minimum cut, and minimum cut we'll define it in a second, but for certain optimization criteria, quite often this is the exact solution for this is going to be NP-hard. And the reason for that is just because it's just like factorial large number of ways to split graph into pieces. For example, if we just think about two groups, right? Two groups of nodes. Then there are 2 to the power n minus 1 ways to do the split. The reason for that is because each node can be one of two groups, so each node has two options. So it's 2 to the power of n. But then, okay, you kind of want to exclude the situation when you have all nodes belong to one set, that kind of situation. And then, you need to take into account the symmetry because the two groups, it doesn't really matter which group the node belongs to, but it's still 2 to the order of n, right? And that's just for bipartitioning. Now, if we start talking about, partitioning into more, even into more groups, there are even more ways. So it's just factorial large, and you literally just cannot go through all the possible options, right? You just cannot literally go and check every possibility, every split. So it's combinatorial optimization problem. And typically when you deal with these problems, there are sort of two things you need to do to take care of. So first of all, you need to choose optimization criterion. So what are we trying to optimize, right? When you do this split. And then, select the way we do optimization. As I just said, unfortunately, with this, graph partitioning, it's NP-hard, and exact solution. It's integer programming, so it's exact solution. You just cannot do this on large graphs, non-polynomial time. So what you do instead is you use certain heuristics. You use approximate algorithms. Sometimes you use greedy methods. And then there are other things you need to take into account. For example, you might want to have a balanced partition. So split the graph sort of in a balanced way. Balanced means the sizes of the parts are approximately equal, or or not, right? And the other thing is you might think of, two-way partition versus multi-way partition. So splitting into two pieces or more pieces. We're going to address this in a minute. But why would you want to do this kind of splitting of the graph? Well, this is quite old problem. In fact, people worked a lot on this in 70s, 80s, and even 90s. And the reason for that is when you solve a lot of equations on the graph, on the grid, you want to partition them in between processors of the computers such a way that each processor have approximately the same load, the same amount of computations to do, but then you minimize communications between them. For example, you want to find some optimal way to distribute them, but this is a balanced cut. The same thing happens when you design VLSI. For unbalanced cuts, quite often, this is a way to detect communities. And the algorithm we're going to talk about today can be used for community detection, or communities, groups of nodes that are more tightly connected among them than with the rest of the graph. Now, speaking about various algorithms, well, there is a greedy optimization. We're not going to talk about it. It's typically not used a lot. It actually used to improve the solution, but not used on its own. Approximate optimization, this is what we're going to spend some time today on, and this is spectral graph partitioning. In fact, it's extremely famous algorithm in linear algebra due to Fiddler. It's has a Fiddler Vector. It's 1972, and then it was sort of rediscovered in the 90s, and then became very, very, very popular after the paper by Shi and Malik, who used it to solve image segmentation problem. So that was pre, deep learning time, and image was converted into the graph, and then you use graph partitioning to segment objects in the image. And then there is an algorithm which is called randomized cut, randomized mean cut. There is this absolutely famous David Carver algorithm, and we're going to talk about it simply because it kind of paves the way to many more modern algorithms. And then there are some practical heuristics algorithms. One of them is famous METIS, multi-level graph partitioning, which is it just works well. And if you want to split graph into multiple pieces, that's usually the software and the algorithm you go after. Now, before we continue, let me jump back to this picture and show you the following. For example, let's say again, as we discussed at the beginning, we're going to split this graph into two groups, right? Here and here, right? Now, if this is a partitioning that we selected, then in fact, to get this partition, what we could do is, we could cut these two edges, right? And that will split the graph. So instead of me drawing and selecting partitioning like that, I can just say, okay, look, this is a split, and then there is this nodes on one side and nodes on the other side. Or I can say, okay, look, this is another split, right, etc. Now, notice that when I do this split, it's also called cut, I cut through two edges. And so it costs me two edges to split the graph, right? I need to remove two edges to split the graph. And that's called a cut, and this is a cut size. Or I can, for example, do this, and then it's 1, 2, and 3 edges. So this cut has a cut size of 3. Or, again, I can just do this, cut out that edge, and then this particular cut has a cost, or it has a cut equal to 1. All right, so that's cut. Notice that the way I just described it, when I do this cut, the sizes of the partitions can be very different. So for example, the cut I just did right now is very, very unbalanced. The size of this partition is 1, and the size of this partition is the rest of the nodes. Now, the size of the partition is usually measured by the number of nodes in that partition, right? Or if I do, for example, this cut, then the cut itself is 2 edges, right? The value of the cut is 2, and one partition is of size 1, 2, 3, 4, 5, and the rest is the rest, right? And or if I do it this way, oops, uh-oh. If I do it this way, this will be more or less already a more balanced partition because this size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and approximately the same on the right-hand side. So in all these cases, the size of the cut was 2. I cut at 2 edges, but depending on what cut I do, it can be more balanced or less balanced. Okay. So these are what the cuts are, right? This is a cut. Now, how do we use this? Well, we can actually, as I discussed, we need to select the way to optimize things, then we need to find out what we're actually optimizing. So if we just split graph into 2 parts, right? Two sets of nodes, V1 and V2, we can define just the graph cut. And I just explained it to you that the graph cut by itself, it's just the number of edges, right, that connects one partition with another partition, right? So if we have this one partition, another one, and there were some edges connecting it, right, and then we cut it, well, that's the size of the cut. That's a graph cut, right? I and j belongs to different sets, V1 and V2. But as we also noticed, sometimes you might want to try to have a balanced cut, right? So you want to make sure when you do the split, the sizes of the partitions are, approximately equal, right? Or not differ too much. So to do that, instead of just using graph cut, we can try to normalize it by the size of the partition. And for example, there is this notion of ratio cut, which is the cut, which is the number of edges that we remove when we separate partitions, divided by the number of nodes in one partition. And so here's another one, right, to make it symmetric. Now, that one works, but not really well. Here's another idea. The other idea is called normalized cut. Now, normalized cut is the following. It is the ratio of, again, number of edges divided by what's called volume. Now, the volume of the partition is the sum of all edges that starts in that partition. So the edge can have both sides in the partition. So it can be this edge that sits within the partition, or it's the edge that starts in the partition and ends sort of in another partition. That's the volume. And that volume is equal, in fact, just if you think about it for a second, it's the sum of the node degrees within the partition. Now, why is that better? Why does it work better? Well, in some sense, because here we divide number of edges by the number of nodes, right? So in some sense, sort of apples and oranges. Here, we divide number of edges by the number of edges. So here is the number of edges in the cut, number of edges that we remove, and this is number of edges that are emanating from a partition, right? So you normalize edges by edges. That makes this metric better. And in fact, this metric normalized cut has also very nice representation in linear algebra. Now, finally, there is a metric which computer science theoreticians love, and it does have a lot of cool properties. It's called conductance or quotient cut, and it has the following value. It is cut divided by minimum of those two volumes. Now, in fact, most of the time we're going to be using this metric or this metric. Now, this one, again, it has a very good theoretical properties, but it's not, not used a lot in algorithms by itself. You know, any guesses why? What can be wrong with this? I mean, in fact, there is nothing wrong with this metric, but since it has the minimum function, it's not differentiable, right? And so then it makes, it's challenging for some algorithms to handle it. So that's the only literally reason it's not, and it's not easy to, represent it directly with say linear algebra. So we will use this partially in the algorithm to verify things, but it's not used as an optimization criteria. So moving along, first I want to spend some time on this, on the David Cargurus algorithm, because it's extremely simple. It's actually amazingly simple, and it works. It's as sort of part of the family of randomized algorithms, you can sort of think of some similarity to Monte Carlo methods. Again, this algorithm actually works on its own, but it also is a basis for a lot of other algorithms. So the idea is the following. We want to find the optimal cut, want to find the minimal cut. So let's select as an optimality criterion graph cut. And so we want to find a cut that is the smallest, right? So we want to split the graph into two parts, minimizing the cut, right? That's the only thing we want to do. Now, the challenge here, again, is there's 2 to the power of n possible configurations. So you just cannot go through all of them, right? So you need to somehow find it without checking all of them. So the idea of Cargurus algorithm is actually simple and beautiful. And it's based on what's so-called edge contraction. So look at this picture. We have an edge here. And then what we do is we remove the edge and merge 2 vertices into one. Okay. So when we merge vertices, some edges becomes parallel. That's absolutely fine, right? Okay. So that's the process of edge contraction. Now, Cargurus algorithm is extremely simple. It just says, pick up a random edge and merge and do contraction. And then pick up another random edge and do contraction. And then pick another random edge and do contraction. And keep doing it until you end up with 2 nodes and some number of edges between them. And this number of edges will be your graph cut, right? Will be your minimum cut. Now, it sounds a little crazy, right? Why would this algorithm actually work whatsoever? But you can prove that the probability that doing this type of process, following this process, this procedure, you'll get the minimum cut is this probability is greater than 2 divided by n squared. Now, if n squared is, and n is the size of the graph. Now, if n squared is large, it's a very small probability, right? You're not going to be happy with this. But what you can do is instead of running this algorithm, because it's very fast, you can run it, at least n squared time or order of n squared time, and then you get some quite meaningful probability that you get the right answer. So you run it many times, and then out of all those, on every run, you get your minimum cut, and then out of all those different minimum cuts you get, I mean, you get the candidate for minimum cut, right? It's going to be this guess by the algorithm, and then out of all of them, you just choose the smallest one. And that's going to be your sort of real minimum cut. And then you'll have a pretty high probability that this is true minimum cut. And and you only need to run this sort of n squared time, so it's polynomial time, so it actually not such a big deal. Versus, of course, 2 to the power n of all combinations you would need to do if you try to search exhaustively. So what does it look like, the algorithm itself, right? So the algorithm is the following. Again, you just go through multiple iterations, and on each of them you pick your min cut, and then you select, on all the iterations, you select the one that is optimal. Now, and what the process is, guess min cut, well, that process is just as we just described. You pick up a random edge and you contract on that. And then you return what sort of the pair that left, and you calculate the value of that cut. So what does it look like in practice? Well, here is an example. I borrowed this from Wikipedia. So notice we picked up, it's a randomized, and each row is its own, separate run of an algorithm. You randomize here, and you start contracting. So this is first contraction. It happened here. Then, for example, algorithm picks up this edge and contracts it. Then it picks up this edge and contracts it. Then picks up this edge, and so on. And eventually, you're left with these 2 nodes and bunch of edges, right? Then there is a second run, then there is a third run, fourth run, fifth run. And notice that depending on the run, right, because it's a randomized algorithm, you'll get different number of edges. Here there are 4 edges, here is, I don't even know how many, here is 4 or 5, and this one on the 5th run is actually found 3 edges, right? And looking at this graph, yes, this is minimum cut on this graph, right? This is the smallest cut you can get here. It's 3 edges. So it's found here in 5 iterations. Theoretically speaking, you need more, of course, to to get this answer, especially since you don't know what minimum cut is. You just do it again multiple times, but you select the run that gives you sort of the winner, the smallest number, and that's it. I mean, it's beautiful, very simple algorithm, easily parallelizable, and again, it's the basis for a lot of algorithms out there. Any questions on this algorithm? All right. So moving ahead, now we're switching from this sort of randomized graph partitioning to more of a linear algebra approach to graph cuts. And this is the algorithm that proposed by Fiddler in 1973, and then again reinvented in the 90s. The idea here is the following. And I'll go a little slow here so you will catch the idea. So let's say we split, we have partitioning, right? It's called, we split the graph. We want to split the graph into 2 parts, and it's V plus, V minus, partitioning of all the nodes. And let's say we have a line graph, right? The way, I showed here, it's a line. And what we're going to do is the following. Let's say the partition that we have is right here, and these are nodes belong to, so 1 partition, and these nodes belong to sort of, say, plus partition, and this is a minus partition. Now, what we can do is, since it's a partitioning, right, it's a positioning of a node into, dividing nodes into 2 groups. For each node belonging to a group, we can assign an indicator. And let's say the nodes that belong to group that we call, say, minus group has an indicator -1, label. And those that belong to the plus group has a label or indicator +1. Okay, so it's just an indicator vector. So the vector is the length of the number of nodes in the graph, and it has minus ones for those nodes that belong to one partition and plus ones that belongs to another. Now, let's go back to the definition of a cut. And remember, cut is a number of edges that crossing crossing the partition, right? What's interesting is what we're going to see now is that you can express the value of the cut through those that indicator vector. Look, if two nodes belong to the same partition, then their values are equal to 1 or 2 minus 1. And then the sum is equal to 0. Now, if nodes I and j belongs to separate partitions, then one of them is, for example, equal to 1, and this is equal to minus 1. And so you add them up, it's becoming 2 squared is 4, divided by 4 is 1. Or if it is minus 1 plus 1, the same thing. So this sum, in fact, this sum is calculating the cut. It calculates how many edges crosses the cut. And then here I sum over all the edges that crossing the cut. Well, instead of doing that, I can actually just put in adjacency matrix. I need to divide by 2 because, to take into account the symmetry. It's undirected graph. And then I can simplify this a little bit. Simplify it a little bit. I bring in the Kronecker delta symbol, which is equal to 1 when I is equal to j, and 0 is when I is not equal to j. And keep simplifying, and I get this expression. Aij is adjacency matrix. Ki is the node degree of node I. Delta ij is equal to 1 when I is equal to j, and 0 otherwise. And si and sj, this is our values. Now, you can actually write this because, look, delta ij, if I write this in the matrix notation, it really says that it is 0 everywhere except for the diagonal. And on the diagonal, you have degrees, right? So it's going to be k degree of one node, degree of another node, and degree of a last node. And this is the matrix itself. So you can write the cut in terms of linear algebra as the following expression. Dij, which is a diagonal matrix with degrees on the diagonal, and Aij is the adjacency matrix. And Si, Sj, those indicator vectors, indicator vector, and the values take +1 or -1. And when you add up this sum, you get the value of the cut. All right. So in terms of linear algebra, cut can be expressed this way. Does this make sense? Okay. So next step. So what? Well, there are a couple of things. First of all, this matrix has its own name, and let me go back for a sec. So there is a matrix here. Dij minus Aij. So it is diagonal minus adjacency. So this matrix has its own name, and it's called graph Laplacian. And it is diagonal minus adjacent matrix. And it can be just specified by itself is, you take on the diagonal, you have a node degree, you have -1s of diagonal, it's unweighted adjacency matrix, and you have 0 everywhere else. So if I actually look at this graph itself, right, you can have an adjacency matrix for this graph, which is, it's going to be only ones for the nodes that are connected. And then the Laplacian matrix looks the following. On the diagonal, we have node degrees, right? The node degree of node number 1 is 1. Node degree of node 2 is 2. Node degree of node 3 is 2. Degree of node 4 is 2, etc. And then it has -1s for each edge. All right. So this is Laplacian matrix. And it's actually very, very useful if you want to study graphs. So Laplacian matrix or graph Laplacian. Now, the way then we can write down the cut in terms of this matrix, and it can be written this way, or if we use notations, vector notation, matrix notation, it's just a quadratic form. So if you think about this, this is a vector S, then there is a matrix, and then there is a vector S, right? So you multiply them through, you realize you get a number, and this number, so it's a horizontal vector, like row vector, matrix times column vector, and you get your number. Uh-oh, my battery is not working. So you get a number. Now, remember we started by looking into the problem of optimizing cuts. And so in this case, what we can do is we can look into optimizing the value of the cut, and then it's going to be a minimum cut problem, right? So then minimal cut is trying to find minimum of this QS value. Now, what we want to do also is we want to try to have, for example, a balanced cut. So we want to make sure, and balanced means we want to have it. We want to have the size of the graph, the size of each partition approximately equal. And for that to happen, I want to introduce a constraint that's going to be adding up all our values and equate it to 0. Now, remember, if the node belongs to one partition, it is +1, +1, and the nodes that belongs to another partition, it's -1 and -1. So, and say another -1. So if we want to have more or less balanced cut, which means the sizes of those two groups are equal, then the number of pluses should be equal to the number of minuses, and if you add them up, they should cancel out and become 0. Now, it will not necessarily be always 0, because you might have, say, odd number, right? But you want to try to push it. All right. So now what we have done is really we just expressed this cut problem as integer minimization problem, right? So we said, okay, we have a function we want to optimize, and we want to find the value. We want to find this S vector, the vector that consists of 1s and -1s, such that this value is the smallest, and these are the constraints. So it is an integer minimization problem. Okay, well, honestly, it's not helpful to us, right? Because again, integer programming, it's again NP hard. So we just expressed the graph partitioning problem as an integer programming problem. But then there is this trick that Fiddler proposed that changed everything. And the idea is so-called spectral relaxation. And the idea is to go from this discrete optimization problem where the vector of those S's +1 or -1 is actually replaced and relaxed to be a continuous problem. And those S's are replaced by just x value that x can be a real number. So we replace discrete with continuous. Now, if you remember going back several lectures, when we talked about, say, we looked for some distribution functions, and we kind of did this trick of going from a discrete summation to continuous integration because it was much easier to work with continuous variables. Well, here it's kind of sort of the same idea that instead of working with discrete variables, we go to continuous. But here it also has a sort of makes it incredible difference, because in discrete variables, this is NP hard. In continuous, it's easily solvable, right? So we couldn't solve it in integer programming. So the idea would be to replace these integers with a continuous variable, replace s's with x, where x values can take, any values, doesn't matter, not necessarily plus or minus 1, but, sort of whatever you get there. And then at the end, we can sort of round it up to plus or minus 1. And that's called the relaxation process. So we replace discrete, precise, exact, discrete problem with approximate continuous problem. And then instead of this integer programming, integer optimization of minimizing this, we will be doing that, right? So you would say, what the difference? It's all the same. Well, the difference is that s is integer, right? And can be only plus or minus 1. And x is a real number, right? And s belongs to integers. And that makes world of a difference, because again, this problem is NP hard. This is easily solvable. And then as a sort of after the solution, we will just take, for example, the sign of x and convert it into s. So we take the solution and take it back to integers. Now I'll pause here. Questions? Does this make any sense to you guys? In terms of math, this is probably the most challenging lecture. All right, I'll continue. So, but now, we actually, have a home run, because now it's a, constraint optimization problem. So we want to minimize quadratic functional, right? It's x transpose Lx under the constraints. Well, how we do this? There is this absolutely standard way of doing so by Lagrange multipliers. So, to find this solution, we'll take this the function that we want to optimize, and then, we put constraints into Lagrange multiplier, and we'll keep this one constraint outside. It's just easier to do it that way. Now, if you remember, when you have this Lagrange multiplier, what do you do to solve the problem? How do you guys solve the constraint optimization problem with Lagrange multipliers? What do you do? Okay, maybe my sound is off or nobody is talking. So how do you solve a constraint optimization problem? All right, so what you do is you just differentiate it, right? What you do is you have to take a derivative with respect to your Lagrange multiplier, and another derivative with respect to the variable that you're solving for. Now, derivative with respect to Lagrange multiply gives you back the constraint, and derivative with respect to the variable you're solving for give you an eigenvalue problem. Take this and differentiate it, you get lambda x, differentiate by x transpose, you get lambda Lx on the left-hand side, you get lambda x on the right-hand side. And that's pretty much it. Now, if that's the solution, you put it back into here, and your answer going to be is this. Now, what's interesting that for Laplacian matrix, the solution that is the smallest one, the smallest eigenvector, is actually a trivial solution. Now, it's solution of all ones, and I'll just give you an example here. If we go back for a sec toward this matrix, notice that if I multiply this matrix by a vector of all ones, then what do I get there?
0.
Zeros.
0. So you're going to be 0 times, you can do 0 times all ones. So, which means all ones is an eigenvector with eigenvalue 0, right? And well, but that's sort of the way the matrix is done by design. Notice that the sum of all the elements on the on each row is equal to 0, and so that's why it works. So, because of that, the first smallest eigenvector, right, is 0. And I'm sorry, eigenvalue is 0, and smallest eigenvector is all ones. But notice we have a constraint saying that the solution has to be perpendicular to a unit vector, right? It has to be perpendicular. So this solution doesn't work for us. So since we're looking for the minimum, right, we want to minimize this functional, and the smallest one, right, doesn't work, what do? Well, you take the next smallest. And so it's a second eigenvalue and second eigenvector. And that, that solves our problem. And so this second eigenvector, second eigenvalue, is actually called the Fiddler Vector. And it's used for the spectral graph partitioning. So it's second smallest, and the reason it's second smallest because the first smallest eigenvalue is equal to 0, and eigenvector is trivial at all ones, right? And since it all ones, it would mean that there is no partitioning, there is only one partition, right? Because remember, eigenvector has a meaning of an indicator to which partition the node belongs. And if it all ones, it means all the nodes belong to the same partition. And that's why, it's not interesting for us. So that's why we're looking for the second smallest eigenvector and second smallest eigenvalue, corresponding eigenvalue. All right. Okay. So here's an algorithm. It's called spectral graph partitioning. What you do is you literally take your adjacency matrix, find the diagonal, compute Laplacian matrix, and solve for the smallest eigenvector. And that smallest eigenvector, then you set up indicator as sign of values in that smallest eigenvector, and that's your solution, that's your partition. Those that will have +1 will go to one partition, those who has -1 will go to another partition. It looks like magic, but you saw the math. Now, what's also extremely interesting, that if instead of this equation, you're solving that equation, right? So this is the same eigenvalue problem, except for here you got diagonal matrix. One can show that instead of minimizing the cut, you'll be minimizing the normalized cut. Let's go back for a second to the beginning of the lecture. So if we just solve simple eigenvalue problem, we're minimizing this cut. And if we solve the eigenvalue problem, which is Lx lambda diagonal matrix X, and here we're solving Lx where L is Laplacian equal lambda x. Okay, so the first one gives us cut. The second one gives us normalized cut. I didn't show it here, but you can check in the papers how to actually derive that. Now, why is this important? Why is that important? Well, because if I look at the partitioning itself, and let me go back to this picture, cut means number of edges, right? And in fact, this is a very good cut because it's equal to 2. But if I run an algorithm that want to find minimum cut, it's not going to find this one. It's going to find the minimum cut. And what's the minimum cut here? Okay, remember, cut is a separation of a graph into two parts. And it's just number of edges that connects two parts. And minimum means I want to find the separation that cuts the minimum number of edges. So in this graph, what's the minimum cut?
The left downside?
Yeah, so I can cut out one node. It's a cut, the value of the cut will be 1. And that's going to be minimum cut. But this partition is not really what you want because you just cut out one node. So you've really done almost nothing. And that's why it's very important to actually have this balancing constraint, trying to make sure that maybe you get the cut, the number of edges is not the smallest, but it kind of balances partitions, right? The size of partitions are similar. And for example, this value of the cut is equal to 2, but it's much more preferred cut for you because it balances the partition. And looking at the formulas, you realize that yes, this one, normalized cut, it does tries to, instead of just optimizing the size of the cut, it optimizes the size of the cut divided by the volume, which is the number of emanating edges. So it tries to balance it. And so this is much better, much better function to optimize. All right. So going back to the solution, now that's an algorithm. Now let's look how it works. Now you have seen this graph before. This is a karate graph. We want to find the partitioning. Now, what you have here is the following. On the x-axis, it's just a node number, right? It's a vertex on node number. The first node, and the first node, the 30th node, 31st, 32nd node, right? 33rd, 34th, right? There are 34 nodes here. Okay, so these are those nodes. And what I have here on the vertical axis is the value of that x vector. So we solve this normalized cut problem, and this is a vector. So for every node, there is a value, right? Node number, I don't know, 30 has this value in this eigenvector. Node number 34 has this value as an eigenvector. Node number 10 has this value in eigenvector. Node number 1 has this value. So it is minus 0.2, and here it's 0.2, and etc. Does this picture make sense?
Yes.
Okay. Now, what do we need to do if we want to divide this, if we want to partition this graph into two subgraphs based on this Laplace matrix, based on this algorithm? What do we need to do, guys? Remember, indicator vector S, we defined indicator vector that tells us which partition the node belongs to, is
Just
defined
split by 0, right?
Exactly. It's just a sign of X. So what we need to do is we should say, okay, look, every nodes that has values, above the 0 line, right? Above the positive, they will belong to the partition, plus, and this belongs to partition minus. Okay. All right. So let's see how it actually works. I'll just do exactly this. I color coded based on that, and notice what happened. It actually nicely split the graph, and we're going to use at the results of community detection of this graph later on more in the following lectures. But here is, it's actually found the split. All right. So that's how it worked. Now, but then there is actually even more interesting story here. That makes this algorithm actually quite fascinating. So this is a second eigenvector, right? This is a picture we just saw. Let me do this. Let me take this vector and permute it such a way that, xi plus 1 is greater than or equal than xi. So what I want to do is I want to renumber the nodes such a way that, the further the node, the larger it is, the larger the value of eigenvalue is. So I take the eigenvalue vector, I sort it, and then renumber the node based on that sorting, based on that ordering. Is it clear what I'm trying to do?
Mm-hmm.
Okay, so I want to permute it. And then very interesting things happen. If I do that, then this is the picture I get. Notice that we, in fact, got the gap here, right? So far in our story, that was, one cluster, one partition, and this is another. But we also got a gap here. So there's a gap here, which is obvious for us that this is split, but there's also a gap here. So there are a couple things happens. One thing is that we can actually, assume, put a hypothesis that in fact we should not only just look at the zero split, but we might look for the gaps. And in fact, this is a one-dimensional embedding, and those of you who are big fans of deep learning realize that what we have done here is literally sort of principal component analysis type of out-in-quarter, but just instead of just using sort of typical usual matrix, we used Laplacian matrix. So that's 1D embedding, in fact, but discovered in 70s. All right, now what do we do with this knowledge? Well, before we go further, let's kind of verify with this cut metric. Notice that if I ordered the nodes, right? Let's say I sorted it. I can, in fact, now very easily say the following. I can say, look, let's split graph here and make sure, let's say the first two nodes will be one partition and this will be another partition. I can do that. And when I have this partition, I can measure the value of the cut. Right? I can measure how many nodes how many edges I cut here. So literally, I'm saying is, take out. Let's say the partition is node 1 and node 2, and the rest, and let's calculate how many edges I cut. And I can also calculate normalized cut and all other metrics. And then I say, okay, let's take node 1, 2, and where the hell is 3? So I can take these 3 nodes as one partition and the rest. And then I can say and measure the cut, right? And then I can say, okay, let's do this as one partition and the rest, and that's a cut, right? And then I can, go on and on and on and say, okay, here is my other next cut, right? And calculate the cut value. So if I do so, That's what I'm going to get. So this is a node, right? This is, and here when I do a cut, that's the value of of you know cut function, cut value. So here is, it's, if I split it here, that's going to be the value, right? If I split the graph in here, that's how much a cut will be. If I split the graph here, so take one partition, another partition, that's the value of the cut. And by looking at this, it's obvious that the smallest value of the cut will be when I split the graph here in those two pieces. And that's going to be the optimal, the smallest cut value. Now, but if I look at normalized cut, and this is the function we're actually optimizing, you realize, yes, again, this is the best place to split, right? This is the smallest value of the cut, right? This is sort of the optimal partitioning. This is going to be one group of nodes. This is another one. Again, this picture is possible only because I permuted the nodes and I put them in sort of in a particular order, right? Then there is this ratio cut, and this is conductance. By the way, notice that conductance has a very, very sort of sharp minima, which is good property. But also notice that there is something happens in here. So there is a possibility that there might be sort of another good cut or another cut right there. Okay, so that's pretty much how algorithm works, right? And that's just proves to you that, yes, it really sort of allows you to see and allows you to find the minimum value. This was a cut into two pieces, right? Sort of, it was two-way cut. Now, if I want to cut in multiple subgraphs, what I can do is I can actually do sort of the traditional divide and conquer approach, where we take the graph, we split it into two pieces, right? Let's say that the cut, and then work separately with left side and then separately with right side. So we run algorithm first here, then the third time here. And if I want get smaller pieces, I just keep cutting. And in fact, this is how you determine how you find communities or clusters. You take this split, and when you split the first time, you get two large groups of nodes, which are not really clusters or communities. But when you keep descending, keep going down more, you eventually get to small groups of nodes that are very tightly connected to each other, and that if you cut them, it will cost you a lot, so you stop cutting. And that's called multi-level spectral partitioning, or recursive partitioning. And that's what, in fact, it's actually one of the most powerful algorithms for community detection or for bipartite graph partitioning. Now, what's also interesting is sort of illuminating is this picture. Let me explain it slowly. I hope you will understand, because this is honestly, when you have a large graph, this is honestly the best way to see with your own eyes groups of nodes, the clusters in the graph. So let me explain. What you have on this first left graph is just their adjacency matrix of a graph, right? And it's pretty large. And blue color just corresponds to an edge in the graph. And so you realize that there are a lot of edges everywhere. Now, I run this normalized cut algorithm once. And then I take this eigenvector that I get, and the same way as before, I permute the nodes in such a way that they're now sorted in the order of increased values with an eigenvector. And that's what I get. Now, how do we interpret this? Look, it just means that the nodes from 1 to whatever, I'll just make it up to, let's say, 100, they're all connected to each other. They're very much connected. They're forming a cluster. And then there is this set of nodes say from 100 to, I don't know, 500, that are also connected with each other. And they're not connected, almost not connected here, and barely connected to the rest of the graph. And then there is this larger group of nodes that are also connected among themselves, but almost not connected to these guys. So in some sense, if I want to do cuts, well, this is, this is my cut, and this is my cut, right? Because that will split the graph into 1, 2, 3 groups. There are a lot of connectivity here, a lot of connectivity here, and quite a few connectivity here. But what's interesting is if I continue working on this the same way on the multi-level as I described the multi-level partitioning scheme and keep splitting, then after a while I get to this picture. So what happens here is these guys are not changed, but you start getting even more details on this picture. So what was happening is I permuted only that part by solving again eigenvalue problem there and reordering the nodes. And you start seeing more and more clusters. And so what it does, this visualization, it actually allows you to see clusters or groups of nodes that are tightly connected within the group, right? Because this connected only to the node within the same group and not connected to other. So this embedding, or this one-dimensional embedding, and then permuting based on that embedding, allows you to very clearly see clusters that exist in the graph. Group of nodes that are connected among themselves. Again, remember, this block really means that these nodes connected to among themselves, right? Because on both axes, it's node numbers, right? And these nodes are connected among themselves, and this group connected among themselves. So that's the power of Laplacian algorithm. Again, Laplacian embedding, Laplacian graph partitioning. It's not only the fact that you can find the split and divide the graph into two pieces, but it is also extremely powerful visualization technique where you take the graph, you permute the nodes, you reorder them based on the values within the second eigenvector, and then it illuminates, it shows you on the matrix visualization nodes that are next to each other as blocks. Is this clear? Or sort of clear? All right. Okay, good. I think you might have similar assignment in the homework of actually, using not doing multi-level, but doing just single one level. It actually becomes much cleaner and clearer understanding if you actually try it, once yourself on the data. And just as always, the references again, just sort of curiosity wise, this is the original Fiddler paper on this Fiddler vector, second eigenvector, and then it was kind of recovered for partitioning matrices in 90s. And then there's this sort of famous paper in computer vision that applied it to image segmentation. All right. Okay. And that's it for today. Thanks, guys. If there are no questions, and remember, there's no seminar today. And we're done.